population, what they're getting at with that is that it doesn't matter what the shape is. So of any shape, I'm going to add that to this. With mean of mu and I'm not entirely sure why they use this word in here, finite standard deviation sigma. I understand the word finite, I just don't know why it's in there. So draw an SRS, simple random sample of size n, from any population of any shape with mean mu and finite standard deviation sigma. So the any population that's the shape part. The CLT says that when n is large, the sampling distribution of the sample mean, x bar, sampling distribution of the sample mean, x bar, is approximately normal.
It's going to be approximately normal even if like something is very one way or the other. Skewed.
Yes, that's right. That's right. That's exactly what this says. You're understanding it perfectly, Peyton. So what's going on here is there's a few things in here that I want to decode for you. One of them is to remind you what the sampling distribution is. That's many, many averages from samples of the same size from the same population, right? That's what a sampling distribution is. It's many, many sample means, okay? Now, when n is large, the sampling distribution of the sample mean x bar is approximately normal. Well, what's large? I don't think the book says large, or what large is anywhere, but I'm going to define that for you. It's not as large as you might think. Anybody any guesses or remember from the other day? What's that? 10%. No, good guess.
30?
It's 30. It's 30. So by the CLT, when n is greater than 30, greater than or equal to, our data is approximately normal. I think I would argue that this is the main theorem of statistics. Now, if I was fancy and I had a whole bunch of computer stuff at my disposal, or maybe I guess I should say if I knew how to use the computer stuff at my disposal, I'd probably pull up something and we'd do a bunch of like little tests and stuff like this. But in your book, this is on page 476, it shows different parent populations that are not normal. So here you've got a uniform a skew right, and that's just a complete mess, right? And what they show, I'm not really sure why they have this sample data line in here, but what they show is if you do a bunch of samples of size 2, this is what distributions would look like. So this is picking 2 a whole bunch of times and finding the averages. So you can see that they sort of look a little bit like their parent populations with a sample size as small as 2. But what happens when you increase the sample size to something that's approaching 30? What do you see in these patterns? Much more normal, right. So that's why the central limit theorem works. It doesn't matter what the parent population looks like. Not at all. If we don't know, as long as our sample size is large enough, it's going to fit into a normal or approximately normal pattern. So this guy is big. It's a big deal. And let me kind of tie it into what we've learned so far. A few days ago we learned about proportions, right? And in proportions we learned that if n times p is greater than or equal to 10, and so this is the likelihood of success, the number of successes, and n times 1 minus p is also greater than or equal to 10, we learned that that is normal. Our sample size is large enough for us to call it normal. Well, for counts, we have the central limit theorem. Yeah, Kate.
When we're looking at the graphs again,
Uh-huh.
it says distribution of means n equals 25.
Uh-huh.
So what exactly does that mean?
What that means is that what you're seeing in that graphic is you're seeing many, many, many samples of 25
Taken from the same population.
taken from this population
Oh, that one.
and averaged, yes.
Okay.
And you get this, and the same thing here, and the same thing here. If you take many samples of the same size, then you'll get that normal curve. As long as the sample is, I'm surprised they're using 25 here as an example. I would have thought that they would use 30. But you can see that even at 25, it's starting to look pretty normal. Right. So what if the parent population is already normal? What if you already know that it's normal? You don't need the central limit theorem. If you don't know what the parent population looks like, then you need the central limit theorem so that you can standardize. So, like, if your sample size is 5 and you don't know what this, and let's say you know it's a skew right that 5 was taken from, you can't standardize, not reliably. But if your sample size is 30, then you could, yeah.
Is this central limit theorem is a way to put the data in a form that always can be standardized?
Correct, basically. So if you were doing an experiment, like we did our experiments in this class, and I said, I'd like to see you get like 20, right? Get 20. We really couldn't have standardized those values that you got realistically for 2 reasons. One, I don't think anybody did an SRS. That's pretty tough to do, right? In reality, in a high school setting. And 2, you didn't have a sample size large enough to be able to guarantee that it was normal, right? So we would be really limited in what stats we could actually apply to the values that you got based on those 2 things alone. But if it was if it was a normal population, if you knew the population was normal, then the 20 is fine. as long as it's an SRS. Yeah.
The finite standard deviation, so due to the fact that the CLT, if we use it correctly, will always give us a normal population,
Mm-hmm.
is the finite standard deviation just kind of describing it as there will be finite and set apart standard deviations that you can standardize with?
I think that basically what they're trying, I'm not really sure what the word finite is getting at. I've never seen that in this definition. I'm throwing it in there because the book has it now. Basically, the way I read this is mean and the standard deviation for the population are given or known somehow. Okay, you have to know these to be able to use them. So how they got them, that's not our concern. If they've given them to us, we use them. Okay? All right. So let's look at a couple problems. Let's see. First one I want to look at is number 61. There's a number of problems today. It's a pretty heavy day for problems, but 61 is on page 480. And it talks about dead batteries on cars. It's a pretty common thing this time of year, a dead battery, I think. Or at least it's probably more common at this time than others. In this problem, it says a car company claims that the lifetime of its batteries varies from car to car according to a normal distribution. Okay, so they're giving us that it's normal. This is given. Do we need the central limit theorem if we're given that it's normal? No, it's not necessary. Okay. With a mean mu of 48 months. That's a pretty bad mu. That's even worse. Let me try again. Mu. It's 48 months. So that's what they're claiming their batteries, how long they claim their batteries will last. Standard deviation is 8.2 months. And they tell us that a group takes an SRS of 8 vehicles. They put these batteries in 8 vehicles. I think we could assume an SRS even if it wasn't given. And that those X bar is 42.2 months. So SRS is necessary. If I go to the local Walmart, let's say, and I buy batteries for 8 cars, could we consider those batteries an SRS of all the batteries that were produced by that manufacturer? Thank you. And the answer to that question is yes, because we can't really go to like all Walmarts and like randomly select, pick 8 batteries out of all the batteries in all the Walmarts, let's say, right? That's not realistic. So we can make the assumption that this would be considered an SRS. Okay, so the first problem says find the probability that the sample mean lifetime is 42 months or less if the company's claim is true. So I've got 42.2 months minus what we expect, 48 months. We're going to divide that by our standard deviation. But since we have more than one, we have to include that square root of the sample size. All right, did you get about -2? So you can go to table A at this point, but when it's an even number like this, you can also use the empirical rule. You guys remember that one? What percent falls between 1 and -1?
68%.
How about 2 and -2? 95. And 3 and -3 would be 99.7. So we're at -2. If 2 is here and 95% falls between, how much is less than?
On one side or both sides?
Less than would be 2.5%, right? And for those of you planning on taking the AP test, you can use table A here, but the readers like it when you use that empirical rule. The actual table A value might be slightly different than 2.5%. Could be. But that's okay. So we're going to say about 2.5% of the time, we can expect a sample of n equals 8 to last less than 42.2 months. I might have said sample of batteries. Okay. So B asks us, does that give us convincing evidence that the company is that their claim is too long? Is there convincing evidence? Yeah. What do you
I
think?
feel like there's neither because we only have a sample of 8. It's like what's the overall population of owners of the battery? And
So you think the sample size is too small to make that call? Okay. Any other thoughts? Yeah, what do you think,
How do
Peggy?
you know it was 2 standard deviations away again? Both sides. Okay.
Well, because I got a -2, I just put it into perspective of the 2 standard deviations. I don't know. Yeah. This is not part of the problem.
Oh.
But what I'm saying is, if -2 is our focus, is our z-score, how could we figure this out without going to table A?
Okay.
Right? Because we know that in between 2 and -2 is 95%. So 2.5 on each tail, right?
Well, you'd get the same answer if you went to the table A.
Yeah, you're going to
Close
get, or very close to, right. Either one would work. I think in this case you actually get exactly 2.5%, I think. So, but anyway, getting back to the question. So Michael says he doesn't think the sample size is big enough to make that call. I would disagree. Hey, be nice.
Just kidding.
I would disagree. I like the thought. I think he's thinking, but I think that we have pretty significant evidence because our value fell within a 5% boundary, right? Remember what I said? If you're within the top 5% or the bottom 5%, you have significant evidence, right? And we're definitely in that bottom 5%. So yes, I'm going to say at 2.5%, we have significant evidence true. I'm going to say refute.
Did you say no then?
Yep, I'm saying no. Yeah, we have reasonable evidence to say that their claim is too long. Does that mean that their claim is absolutely wrong and there's no doubt? No, probably not. But maybe sample size would come into play if we were going to take them to court or something like that. Maybe. But I don't think so. I think that would probably fly. Probably take them to court and go, I'm going to sue them. Sue them. Sue them. Probably just get, you know, a few bucks back towards each battery. I don't know. All right, there's one more I want to at least set up for you or help you set up. It's number 65. It's talking about an insurance company. Same page. And this one says that an insurance company claims that in the entire population of homeowners, the mean annual loss from fire is $250. Okay. Now, understand that's an average. So some people are going to have exactly zero, right? Most people, and then some people it's going to be a total loss, and there's going to be in-betweens on that, right? So there's going to be lots of different values, but on average, everybody has a claim of $250, and the standard deviation is $5,000. The distribution of losses is strongly skewed right. So we've got a right skew for obvious reasons, right. A lot of people are going to be zero, but then there's going to be some multi-million-dollar home that's going to go up, and it's going to skew it greatly. Many policies have a zero loss, but few have large losses. The company hopes to sell 1,000 of these policies for $300 each. So they hope to sell 1,000, and I'm just going to go just $300 each. I'm guessing that this is probably going to become my X bar value. Okay, the thing that I'm going to compare it to.
Wait, the mean is 250, but the standard deviation of 5,000.
Yeah, that looks a little funny, doesn't it? Yeah. Right. So, I agree. That's noticeably a little funny, but it kind of makes sense in the situation. Those that do lose are probably going to lose quite a bit. Yeah. Okay. Yes. Well, I don't know. Maybe. Let's have a look. So it says, assuming that the company's claim is true, what is the probability that the mean loss from fire is greater than $300 for an SRS of 1,000 homeowners? Yeah, we really can't standardize unless we can say that this is normal. And with this sample size of 1,000, yeah. So we would say this is normal by the CLT. That's really all you have to say. That gets the idea across. You understand that it's bigger. You could do something like 1,000 is greater than or equal to 30. You could do that, but I don't know. No, I don't think so. A. So they want us to see what's the probability that 300 occurs, basically. Now, that's the setup to get your z-score and to get the probability. X bar minus mu over this. And I don't know that you guys would have too much trouble with this, getting that. It's B that I really want to focus on. So I'll let you guys handle that. Let's talk about B. Because I had a number of questions in the first class about this, and there was some confusion as to whether they were switching now to proportions, and they're not. It says, if the company wants to be 90% certain that the mean loss from fire in an SRS of 1,000 homeowners is less than the amount it charges for the policy, how much should the company charge? Well, they want to charge $300. They want to make sure that the loss is less than that so that there's some profit. So what we really want to know is, what would the X bar be? Let's see, the 250 doesn't change. Thank you. But we don't know Z. We need to get Z. And the 90% that's given is how we get to Z. So we have to find 90% or as close as we can on table A and get that Z-score put into there so that we can then solve for the X bar value. So basically what they're saying is we want to make sure that 90% of the time our $300 will be within the amount that we expect to lose. So what is that value where 10% of the time we'll lose money and 90% of the time we'll make money? Does that make sense? So, did you get it?
I think it's 1.28.
I think you're right. Yeah, you're absolutely right. 1.28. So by looking at table A and looking at it backwards, trying to find as close to 90% as we can, 8.8997 is as close as we can get, then we take that Z-score backwards. And it's been a while since we've done one like that, too. So then you're going to solve for the X bar in this case. Just a question. How much do you suppose a person could make working for a company doing exactly this? Yeah, is that realistically hard math? We're not talking calculus here, right? We're talking fairly simple basic algebra. But you have to understand the context and what to do with it, right? Now, I'm not saying that all statisticians just work with easy numbers like this. That's certainly not the case. But there are certainly, I can imagine some companies out there willing to pay quite a lot to know this kind of information. And for what it's worth, the reason I'm not doing this for a living is because, well, I came into the game far too late. So, but you guys didn't. Maybe this is going to be something big for one of you guys. Who knows? Anyhow.